Here's the data of the code you are about to see. Integration techniques involve methods like substitution, partial fractions, and integration by parts. The input data includes the integrand function and the variable of integration. Here's the UML diagram of the code you are about to see. The integration techniques class connects to methods like indefinite underscore integration, definite underscore integration, and apply underscore integration underscore by underscore parts. This modular approach enables flexibility in solving diverse problems. Integration, a bridge between the abstract beauty of calculus and the tangible power of computation. But how do we make that leap? Well, here's how Python does it, elegantly and efficiently. We begin with NumPy. Think of it as our Swiss Army knife for numerical computations. By calling it as NP, we're giving ourselves quick access to one of the most versatile tools in programming, like naming a close friend Mike instead of Michael. Short, practical, yet personal. Now, the heart of our code, the class integration techniques. This isn't just a name, it's a promise, an identifier for solving integration problems. It's where data, UML, and code converge. But what brings this class to life? A method with a double underscore in it, the constructor, the soul of every Python class. It's not just a function, it's the starting line for everything that follows. Look closely at its arguments, function, the mathematical star of our story. Without this, there's no integration, just silence. A and B, the lower and upper limits of integration. Imagine navigating without boundaries, a ship adrift in infinite waters. N, the resolution, defaulting to 1000. Think of it as the pixels in a high definition image. The more, the better the clarity. Now here's the twist. All these variables are tied to self. Why? Because self makes everything personal. It binds data to the object, allowing the class to adapt and thrive no matter how it's used. If we removed any of these, chaos. The code would crumble. Integration demands precision, and every part here serves its purpose. Think about this for a moment. Integration itself is a metaphor for life. By summing up infinitely small parts, we extract meaning, find clarity. Isn't that fascinating? So, next time you write a Python class, remember, you're not just coding, you're orchestrating a symphony where every note matters. And with integration techniques, every piece comes together to compute something greater than the sum of its parts. Now let's upgrade to the next lines of this code. We are doing a really learning. Now that we've set the stage with the class and its constructor, let's dive into the method that begins to give our integration a sense of direction, the trapezoidal rule. This method isn't just another computation. It's like breaking down a mountain into manageable steps, approximating the area under the curve by treating it as a series of trapezoids. Let's examine the key players here. First, X, there is nemp.linspace, self day, self b, self.n plus 1. This line is pure genius. We're generating evenly spaced points between the limits a and b. Picture it as plotting tiny dots along a curve, ensuring no part of the journey is overlooked. Then, y, self, function x. This is where the magic happens. The function we passed earlier springs to life, transforming those points into heights. These heights will define the trapezoids that approximate the curve. But why the trapezoidal rule, you ask? It's a balance between simplicity and accuracy. While not as refined as Simpson's rule or other advanced methods, it's a reliable workhorse, efficient, straightforward, and surprisingly effective for many scenarios. Here's a thought. By approximating with trapezoids, we're making a trade-off, accepting imperfection for practicality. Doesn't that sound like something we do in life every day? With this setup, the trapezoidal rule method is ready to compute areas. Each line in the code builds a step toward understanding how we approximate something infinite, small steps leading to big insights. And this is just the beginning. The trapezoidal rule is a gateway to understanding numerical integration. Stay tuned as we calculate, refine, and uncover the elegance hidden in the mathematics of approximation. All right, let's bring the integration techniques class to life with an example. First, we define the function to integrate. Define f of x, where f of x equals x squared. Then, we create an instance of the integration techniques class. This instance is like our toolkit for solving integration problems. An object integrator is created from the integration techniques class. Its parameters are f, which is the function x squared, 0 as the lower limit, and 1 as the upper limit. Now we apply the trapezoidal rule, print alpha trapezoidal rule, integrator.trapezoidal rule for f. Translation of code logic. We call the trapezoidal rule method from the integrator object. This method calculates the area under the curve using the trapezoidal approximation. Here's how it works internally. Integral is calculated by subtracting self.a from self.b, which gives the interval width. This width is multiplied by the sum of y values at consecutive points divided by 2 times self.n, representing the trapezoidal rule formula. Finally, we print the result in a formatted way, keeping only 4 decimal places. Next, the Simpson's rule. Print at Simpson's rule. Integrator. Simpson's rule. Ref. Translation of code logic. We invoke the Simpson's rule method from the integrator object. This method computes the area under the curve using Simpson's approximation. Internally, it divides the interval self.b minus self.a by 3 times self.n, giving the segment weight. Adds the y values at the start, every alternate point, and endpoint using weighted factors of 1, 4, or 2, depending on their positions. Finally, the integral result is calculated and formatted to 4 decimal places for printing. Bringing it all together. When we run this code, it shows the 2 results. The area under the curve calculated by the trapezoidal rule. The area under the curve calculated by Simpson's rule. This example brings the entire concept into one place, helping students see how these techniques can be directly applied to solve real mathematical problems with ease.